Okay, so continuing on with our state functions, they just depend on the final and initial. However, this is kind of tricky because do we ever determine what the final internal energy is? This is called the absolute internal energy. No. Do we ever determine the initial? No. And why is that? Why don't we determine what the absolute internal energies are? That's because the potential energy term, we don't know where the absolute zero of internal energy is, do we? No, this, and so, this can be estimated, but not determined exactly or with any degree of accuracy. And so, although we don't know what this is, delta U is always the same amount of energy, and we can figure out how much energy that is because delta U is equal to Q, which we can measure, and work, which we can figure out, Q and W. So, each time we do this reaction, every time we do this reaction, the same reaction, we always get the same amount of energy, that is Q plus W. That's a state function. So a state function is very predictable. Every time you do this, you get this amount of energy, Q and W. But there's a tricky thing though, and that is Q and W themselves, these are not state functions. These are what we call path-dependent functions. And path-dependent functions aren't always the same, given the final state and the initial state. So for example here, we aren't always going to get the same amount of heat or work, but we always get the same amount of total energy, that is delta U. And so the amount of heat can vary. The amount of heat varies depending on how we carry that reaction out. That's a path-dependent function. So for example, we could do that reaction in a bomb, or we could do that in the open lab, and that's going to change the amount of heat, but it won't change the total amount of energy changed. And so let me give you an analogy for this. One analogy is just looking at this particular reaction. Let's give this a particular state here, and that is, let's take 1 mole of methane, 2 moles of oxygen gas at 298 Kelvin. Okay, here's my initial state. And the initial state is going to be defined by having some kinetic energy, which is the temperature, that is 298, and some potential energy. The potential energy is wrapped up in all the interactions in here. And this is going to go to CO2 gas plus 2 H2O liquids. Okay. And then there's going to be a energy associated with CO2 and water. And with kinetic, 298 Kelvin, and the potential energy. And we know the energy change. When we combust methane, this should be an exothermic reaction, releases energy. But do we always get the same amount of heat? Well, no. We always get the same total energy change, that is delta U. But the amount of heat we get varies depending on how we burn it. So for example, if we burn the methane in a, one of those compressed natural gas, CNG cars, have you seen those? Those cars, you don't fill up the tank with gasoline, you fill up the tank with this, natural gas, methane. And so if you were to burn it in the car, what you want to do, if you burn it in the car, is maximize the amount of work you get from that. And so the methane goes into the engine and it pushes pistons down, up and down. And so basically, we try to get the most work in the minimum amount of heat. And so depending on how much work you do, for example, the more work you do in this particular reaction, the less heat you're going to generate. And so that's what we call a path dependent, because it depends on how you burn it. The total energy is the same, but not the heat or the work. Or, sometimes we want to maximize the amount of heat we get. So for example, if you want to use this reaction to heat a pot of tea, then you don't want to do any work. You want to do all heat, right? And so what you try to do is you maximize the amount of heat and minimize the amount of work you do. And therefore, you can convert all this energy change into heat, which would better suit you in that particular instance. And so these are called path dependent because, again, it depends on how or what path you took in this particular reaction. Now, some types of work are unavoidable. You know, what type of work is unavoidable? Pressure volume work. That is, pressure volume work is unavoidable because if you do this under constant pressure conditions, you know, gases are formed, gases are consumed, so the volume has got to change in order to maintain constant pressure. And so what we're going to do is we're going to just look at the typical. We aren't going to look at trying to run a car or trying to generate electricity or anything like that. We're just going to look at, you know, how much energy am I going to get from this reaction after doing this work. This work is a mandatory work of a chemical reaction done at constant pressure. So for example, was any work, did any work happen here? Well, when we look at the work, we need to look, okay, from now, we're just going to focus on P delta V work. P delta V work you can't avoid doing it at constant pressure. You can avoid P delta V work at constant volume. So, for example, if we did this in a bomb, then there's no delta V. Delta V is equal to 0, and so all this internal energy change was converted into heat. Okay, from now let's focus on P delta V work. And, well, if we look at constant volume, we do this at constant volume, then delta U here is equal to Q plus W. Well, W is going to be 0, because delta V is 0, and therefore all that internal energy change is converted into heat. This is very good if you're going to heat up a pot of coffee. But what if we did this at constant pressure? So let's look at this reaction at constant pressure. Then work is going to be done, because if I want to figure out how much work, then I'll have to know V initial and V final. So let's go ahead and calculate the amount of work that's done when a mole of methane combusts. And so over here I have, initially I have 3 moles of gas, and it's 24.45 liters per mole under these conditions here. And that gives me a V initial of what? What is it, 7435 liters, correct? V final, I have 1 mole of gas, is 24.45 liters, plus the 2 moles of liquid water. So 2 moles of water, and that's 18.02 grams per mole. And the density is a milliliter, 1.00 grams. So what does this come out to here? So this comes out to 24.45 plus 3604. But there's a problem with this. I can't add these two together because this one's in liters, this one's in milliliters. And so I need to convert it into liters. That is, a liter is 1,000 milliliters. So this is going to give me 24.486 liters. And so I have my V initial and V final. And so I could figure out how much work was done in this particular process. Work is just minus P external times delta V of the system. And so P external is just 1 atmosphere. We'll just call it exactly 1 atmosphere. What's delta V of the system? 1 atmosphere being normal atmospheric pressure. Delta V is V final minus V initial. And so V final is 24.486 minus V initial, which is 74.35 liters. What does that come out to? 4, 6, 8. 49.86. Is that what you get?
Yeah.
Liters. And so, well, this is going to come out to, well, it's a minus times a minus is going to be plus 49.864 liters. Right? Atmospheres. Well, a liter atmosphere, we can convert to joules, is 101.3 joules per liter atmosphere. And so how many joules of work? Well, 4,900 and does somebody have a calculator? 5,051. 5,051 joules, which comes out to 5.0. How many sig figs am I allowed? 4. 5, 1. Give me one more digit.
Well, it's 5,050.8.
50.8. Yeah, we got to show the round off. We always get in the habit of showing the round off. Is 8 rounded or 8's just straight off the calculator?
It's 818.
Okay, that's fine. Okay, so this is going to be kilojoules. So about 5 kilojoules worth of work. Well, you know, if there was 5 kilojoules worth of work, then the amount of heat coming off this is going to be different. You know, if we did this at constant volume, then that all was converted into heat. But now, when we do this under constant pressure, it's going to be different. You know, here. And so, how different is it going to be? Well, we got to look. You know, this Q plus W here. Are we going to get more heat or less heat released from this particular reaction? Well, who did the work, you know? Well, you know, I'm here with V initial, and V final is a lot smaller. And so this system is collapsed in volume, so some of the gas was sucked out of there from the reaction. If you suck out the gas, then what's going to happen is you got a vacuum, and then the surroundings is going to just crush it. And it's like the can. We got rid of some of the volume in there, and the surroundings did the work. And so in this case, the surroundings did the work. And so the work term here is different. It depends, you know. It also depends on the external pressure too. We could do more work or less work. You know, higher external pressures or lower. You know, it depends on the volume changes, etc. All right, so there's a difference in the amount of work we get. I mean, excuse me, in the amount of heat we get, depending on how we do it, the reaction. And so here, you know, delta U, this is exothermic, so this is negative. The heat, you know, it should be exothermic, so heat should be negative. And the work was done by the surroundings here. And so we got to figure out how much heat we get. And so when we look at the work is actually positive here. So if the work is positive, then we get a scenario like this, you know. And so what we're going to do is we're going to look at how much heat we get, because, you know, when we do this at constant volume, delta U is just equal to Q, but when we do this at constant pressure, right, here's our delta U. This is a state function here. Now was the work done by the system or by the surroundings? Yeah, and so in other words, the surroundings loses energy doing the work, crushing can, whatever. Surroundings loses the energy doesn't disappear because the first law of thermodynamics says that energy is neither created nor destroyed. And so where did the energy that was lost by the surroundings go? Well, you'd think it was consumed in doing that work, crushing the can, but it doesn't disappear. The work goes somewhere, that is, the energy goes somewhere, and where does it go? Yeah, if the surroundings loses energy doing the work, then that means the system must have gained energy doing the work. And so the system gains energy doing work. Well, it actually didn't do any work, the surroundings did the work. So the system gains energy, right? And then W plus Q is got to equal delta U. And so Q's got to be this, right here. This is our Q. And so compare the two Q's. Which one generates more heat? Doing this at constant volume or doing this at constant pressure? Actually, oops, this is wrong. Sorry. This is not supposed to be QP, this is supposed to be QV. What does V mean? Constant volume. And so if we do this under constant volume conditions in a bomb, there can be no work because the volume doesn't change. And therefore, delta U is all converted into heat. But now over here, we have to also factor in the work because we're doing this under constant pressure conditions. Doing this under constant pressure conditions, you look at that, and delta U is equal to Q plus W. In this case, W, we get some energy from the surroundings, and then Q is the heat. And so compare which one releases more heat, constant volume or constant pressure? Constant pressure releases more heat. Well, the question comes up, well, how can it release more heat than the total energy? Because, U is the total energy. If U is the total energy and delta U is the total energy change, then we're missing something, aren't we? Because if this is the total energy change, how can we get more energy than the total energy? That doesn't make sense because the total energy should be the total energy, not the partial energy. And so where's that extra energy coming from? Well, it's how we define the total energy. That's the total energy of the system, This is the kinetic energy and the potential energy of this initial, and the kinetic and the potential energy of this final. But what we don't see is this. We don't see how the system interacts with the surroundings. And in this case, because of the volume collapse here, what we do is we're getting energy from the surroundings. And so we have the total energy plus the little bit of energy from the surroundings, and this is going to give us our heat. And so that energy that the surroundings lost gets input into the system, which means the system's going to release more heat. Anyway, this is something to think about. Well, this work is going to happen, as long as we do this reaction under constant pressure conditions, we're always going to have work. And can we use that energy from the work? Well, not necessarily. I mean, the work has got to be done. It's either going to be energy lost or energy gained if there was work done or on the system. And so what we want to do is we want to look at, how can we predict how much heat is going to be produced? Because it depends on how much work you do and what type of work you do. And so let's take a look at one more analogy going back to this heat and work thing. And so, for example, if somebody's on a slide, like a playground slide, and here's U initial, down here's U final, there's going to be some delta U, a change in total energy here, which is this. And in this case, it would be this potential energy, because this person's not moving. Gravitational potential energy. And then let's say they slide down the slide. So as they slide down the slide, they get to the bottom of the slide here, and they've lost a lot of energy. Well, they lost a lot of energy. Where did that energy go? Well, the total energy change here is equal to Q plus W. How much work did this person do? Turns out there's no work done in this particular case. So the work term is 0. And so all that energy was converted into heat. And so the system lost energy, and the surroundings, well, surroundings are going to get hot. The surroundings will be the slide. So if you touch the surface, the metal slide, you touch the surface, you're going to feel heat radiating off the surface here. And so, but the amount of heat changes if this person does work and what type of work. And so, for example, if alternately here, we have the person up here, and there's a rope tied around this person attached to a pulley. And at the end of the rope, we have some kind of mass here, some weight. And the weight of this block is about the same as the weight of the person, maybe slightly less. And then we oil the surface of this so that there's no friction. The friction causes all this heat here. Otherwise, you wouldn't stop, you just keep going. So all that potential energy would be converted into kinetic energy as this person's just sliding indefinitely until friction or heat will slow them down. But in this case, if we oil the surface of the slide, we're going to get minimal friction. And then this person goes down. Well, if this weight is about equal, they're going to go down very slowly. So they go down very slowly. Eventually, they're going to end up at the bottom of this. When they end up at the bottom, well, was much heat generated? No, not much heat was generated because a lot of that internal energy change was converted into work, the work of lifting this weight up. And so here, delta U is equal to Q plus W, but in this case, this is at a minimum. We'll just say roughly 0 or close to 0, and that means the work terms are maximized. And so either, in this scenario, we have it all as heat. In this scenario, we have it as mostly work. We'll have something in between depending on how much work. The more work we do, the less heat, vice versa. And so how can we predict it? How can we predict how much heat? Well, you can't predict how much heat because you need to know how you did the reaction. We can predict delta U. That's not a problem. We can measure delta U. Delta U is equal to Q plus W. But what we want to do is we want to have a predictable amount of heat. And the problem is heat is not a state function. But there's an easy workaround. And so how can you get the same amount of heat each time? Each time you do the reaction. In other words, how can we make heat a state function? A state function just depends on the final initial states, and so we have some reaction. So how can we make heat a state function rather than a path-dependent function? A path-dependent function, you would have to know how it got from the initial state to the final state. Not that it just went from the initial to the final state. And so the answer is easy. You always do the reaction exactly the same way. Each time you do the reaction, you do it the same way, you get the same amount of heat, right? And so you do the reaction the same way each time. In other words, you follow the exact same path each time you do the reaction. If you follow the exact same path, then you'll do the exact same amount of work, which will lead to the exact same amount of heat, and then therefore we can predict how much heat we're going to get from the reaction. And so how do we do this the same each time? Well, you have to make certain restrictions. You got to tell somebody, do it this way. If you do it this way, you'll get this amount of heat. And so, what are the ways that we're going to do this? Well, one of the restrictions, you can do this under constant pressure conditions. Yeah, that's not such a big deal. We do it at constant pressure. And the second restriction is P delta V work only. And so we aren't trying to power a car or generate electricity. This is just the natural work of a chemical reaction. You know, this has got to happen. This type of work has got to happen in order for the reaction to take place under constant pressure conditions. Then we know that delta U is equal to Q plus W. And so Q, if we restrict it to constant pressure, that's going to give us Q sub P. It just stands for constant pressure, P. Is equal to delta U minus W. Now the type of work we're going to do is P delta V work. So that's minus P external delta V system. So this would be the work that's involved here. Well, when we look at delta U, this is a state function. And delta V, if we have a change in volume, let's say we went from 10 liters to 15 liters. Delta V goes from 10 liters to 15 liters. So V initial's 10, V final's 15. Does it matter how you got there? Does delta V change? So for example, if your initial volume is 10 liters and your final volume is 15 liters, does your delta V change depending on, well, if we went from 10 to 1,000, then from 1,000 to 15, will the delta V change? No, delta V doesn't change. It doesn't matter. So delta V is also a state function. It's like temperature. Temperature is a state function. If you had an increase of 10 degrees C, it just depends on your final temperature and your initial temperature. That's your delta T. It doesn't matter if you heat it up to 1,000 and then cooled it back down. If your final and your initial are the same, then your delta T is going to be the same. So delta T, delta V, these are state functions. And so if you look at Q is just dependent on state functions now. Like delta P is a state function as well, and P is a state function. And so now we have Q as a state function. Once it says a state function, we define this as a new state function. The new state function will be change in enthalpy. And so what is enthalpy? Well, I know what U is. U is internal energy, which is the total energy. So what is enthalpy? Partial energy? Well, enthalpy is something like this. This is what we call an enthalpy diagram versus an internal energy diagram. But we have enthalpy here on some axis here. And if we start off with a CH4 gas plus 2O2 gas at 298 Kelvin, and then drop down to CO2 gas plus 2H2O liquids at 298 Kelvin. And then the amount of heat we're going to get from this is called delta H. Delta H is equal to QP with a P delta V restriction. And so what is enthalpy? Well, delta H is a state function. That depends on the final enthalpy and the initial enthalpy. These we call the absolute enthalpies. And so H initial is equal to what? Well, H initial is equal to U initial. Okay, if we look at this over here, it's going to be plus P delta V. Or in other words, U initial minus P external V initial. H final is equal to U final minus P external V final. And so what enthalpy is it's the total energy taking into account what we call the pressure volume state. In other words, when we look at the total internal energy, we don't look at how this system interacts with the surroundings in terms of PV work here. You know, there's going to be some total energy associated with this change in terms of kinetic and potential energy. But with enthalpy, what we do is we look at the total energy and then factor in the PV state. P times V is energy as well, and so we look at the PV state initial and the PV state final. And then we can see, how the surroundings are going to interact with the system. That is the system going to do work and lose energy to the surroundings? Or is the surroundings going to do work? And so this factors in how the surroundings are going to interact. And in the last example we saw, the surroundings did the work, giving energy to the system. So the PV state, PV state allows us to see, how the surroundings interact with the system in terms of PV work. When we factor that out, then we see, what kind of heat or what kind of energy is available. And so another way of looking at this is this. When we look at delta H is equal to delta U minus the work. We're looking at P delta V work. And so the way I like to think about this is our net, our net income or whatever. This would be our gross. And so let's say you had a gross paycheck of $1,000. Are you going to net $1,000 that you can deposit in your bank? No, if you had a gross paycheck of $1,000, then you have to take all the deductions out, right? The taxes, whatever else. And so the work term here, this could be a tax. So you grossed $1,000 and you had to pay $50 in tax, you're only going to get $950, right, because of that. Can you avoid the tax? Unfortunately, you can't avoid the tax. Just like, can you avoid P delta V work if you're going to do this at constant pressure? No, you can't avoid P delta V work if you want to do this under constant pressure. Otherwise, you can't do it at constant pressure. But the P delta V work is not always a tax. Sometimes you can get some extra income. That is, rather than a tax, this could potentially be a bonus. Because if you're the system and you had to do work, then it's going to be a tax because you lose energy doing the work. But if you're the system and the surroundings does the work, then the surroundings loses energy and you gain energy. Maybe gaining energy is a benefit in that case. And so it could be a bonus. Or sometimes, there's no volume change at constant pressure. So delta V and delta P simultaneously are 0. That is, there's naturally no volume change. The total volume initial is equal to the total volume final, regardless of if you do this under constant pressure or constant volume, then it just doesn't impact it. So the work is always going to be 0, because if delta V is 0, then there's no work, right? And so this is one way of thinking about it. And so the net is actually what you can use. If you're looking at money, you aren't going to be able to use all $1,000 gross. So it doesn't matter what the internal energy change is. You have to deduct or do whatever to figure out how much you're actually going to net. So let's look at some constant pressure scenarios. At constant volume, it's much easier, of course, because we don't have to worry about work. But at constant pressure, we're going to look at first at exothermic, and then we'll look at endothermic scenarios. We're going to look at internal energy diagrams and enthalpy diagrams and see if we can understand them. And so in terms of internal energy diagrams, or U, we have U on the y-axis, There's some 0 point, but we don't know exactly where. It was just kind of arbitrary. Exothermic means, there's energy lost initial internal energy is higher, and we'll have a delta U. In order to figure out what the work is, because delta U is equal to Q plus W, and so in order to figure out what the work is, we're just doing P delta V work, right? If we do P delta V work, well, this is also equal to delta H, right? Plus W, or delta H plus a minus P delta V. Well, to figure out the work, we need a delta V. And so let's say here, V initial and V final are the same. So under constant pressure, the V initial is equal to V final. Delta V is equal to 0. If delta V is equal to 0, then the work term is going to be 0. And therefore, delta U is equal to QP, which is equal to delta H. This one, I do this just as a reference because Q is equal to delta H. Well, technically Q is equal to amount times delta H, right? But essentially Q and delta H are saying the same thing. So this is why I leave it like this. And so in other words, if you net 1,000, and let's say, well, let me back up. If you grossed 1,000, you'll net 1,000. Because no work was done. There's no tax, there's no bonus. Gross 1,000, net 1,000. Okay, let's look at this scenario where we go from V initial, let's say V initial is big and V final is small. And so again, here we have our delta U. Our delta U is equal to Q plus W. Now we're going to look at this. Here, this is our QP or delta H. Over here, when we look at our delta V is going to be less than 0 because the volume is shrinking. And so delta V is negative. If delta V is negative, then we've got to remember work is equal to minus P delta V, P external delta V of the system. If delta V is negative here, then the work term will be a negative times a negative gives us a positive. And so the work term is positive. The heat term is negative because it's exothermic. And so in a scenario like this, the system gains energy. The system gains energy by having work done on it by the surroundings, because who did the work in this particular case? The surroundings did the work. We went from a bigger volume to a smaller volume, so the surroundings crushed in the system volume, right? And so the system gains energy by having work done on it by the surroundings. And then the work plus the heat is the equal delta U. And so the heat term is going to be like this here. And so we see Q plus W there. And so in that case, we actually net more heat. We net more heat than the total energy change because we get some energy from the surroundings. And so in this case, the work was what we're going to call a bonus. Work is a bonus. And if we're the surroundings, we're looking at getting that income as heat, and we're going to get more. Okay, in the next scenario here that we're going to look at, we're going to go from a smaller V initial to a larger V final here. And so this will be our delta U here. And so delta U is just equal to Q plus W. But here, delta V is going to be greater than 0 because the system volume is increasing. And then we look at the work. The work is minus P delta V. And so if delta V is positive, then the work term is negative. And so that means the heat term is negative and the work term is negative. And so who did the work in this case? Well, the system did the work. And so the system is going to lose energy in doing the work. So the system loses energy doing the work. And then we're going to have this much heat because Q plus W has got to equal delta U. And so let's say your gross was 1,000, but are you going to get 1,000? If your gross is 1,000, are you going to end up with 1,000 net? Q or delta H. Over here, our gross was 1,000, right? But our net was actually more than 1,000. How did we get, if the total money change was 1,000, how did we get extra? Well, the total money change was for the system, and that was 1,000. The system lost 1,000, and then we got a little bonus, maybe $5 bonus from the surroundings here, which means we end up netting a little more. Over here, well, let's say we had to do $5 worth of work. If we had to do $5 worth of work, that means we had to pay $5 in taxes, and that means we're only going to get net $9.95 in terms of income. Does that make sense? Maybe, maybe not. For most people, it doesn't make much sense. And so you have two choices. A lot of people just give up because they think it's too hard. But it's not too hard. This is just memorizing, just going over it repeatedly until you memorized it. This is one of those things. All right, and so in this case, the work was a tax, a tax. So $1,000 gross, $5 tax, $9.95 net. That would be an example. Okay, and in terms of internal energy, it's fine. We can visualize this because Q plus W is equal to delta U. We just have to add up to that. But we have another type of diagram. The other type of diagram is called the enthalpy diagram. And so we're going to go through the exact,
Can you do an example for previous one? Numerical example?
Which one?
The constant pressure, exothermic.
Constant pressure, exothermic.
Yeah, just to get like a feel of something with numbers.
With what? Which one? Work being done by the system or work being done by the surroundings?
Is there not going to be like any numerical?
There is.
Well, no.
Yeah. We're going to do numerical examples pretty soon. We're just going to go through all the qualitative examples first, and then we'll do some numerical. We already did part of the numerical work right there in calculating the work. We could figure out the work numerically quite easily. Delta U you can determine in different ways. For example, you get that from bomb calorimetry. You can get a delta U. And so we'll do a delta H calculation. But we'll do those after we go through all these scenarios. So these scenarios you should understand before doing one specific example. So this is it. If you do one specific example, then you see one tree in the forest, right? But what we're doing is we're going to see the entire forest, the whole range right now, and then focus in on one tree. And so enthalpy, what is enthalpy? Tell me what enthalpy is. What is enthalpy? It's the internal energy factoring in the PV state. The thing is, okay, are you going to get this? Are you going to get this quickly? Probably not. Are you going to be able to cram this right before the test? No. You know, this is something that requires some work and effort, you know, to get down. Otherwise, it's too much. You know, too confusing, too many things going on. Well, anyway, we're going exothermic again. And so here we're going to have a delta H here. Delta H or QP. Right? Is what we got here. Delta H is equal to delta U minus W. All right, let's see what's happening here. Well, if V initial and V final are the same, then delta V is equal to 0. If delta V is equal to 0, how much work is done? 0. And so delta H is equal to delta U, which is equal to QP. Is equal to QV, technically also. All right, delta, yeah, I should probably write that in here. Delta U is equal to QV. Well, let's say we're going from big, you know, so V initials here, to small, V finals here. And so we have a delta H here. Who did the work in this case? Surroundings did the work. Surroundings did the work, then it's considered a bonus for the system. And so delta H is equal to delta U plus, actually, minus W. Minus W. And so we look at this here. The work is equal to minus P delta V. Delta V is negative. If delta V is negative, then the work term is going to be positive. And so if the work term is positive, that means the system gained energy, right? The system gained energy by having work done on it. And now here's where it's going to throw you off, because if the system gains energy doing work, then I should show it. The system gains energy doing the work, right? System gains energy doing the work. And therefore, the amount of heat released is going to be greater, but this is the amount of heat released. And so, what's going on here? What's going on here is this, and this might be a little bit weird, but yes, the system gained energy in doing the work, and so the work term is positive here, but this is a negative here, right? A negative times the positive gives us, this is going to be net negative term here. And so if this is a net negative term, well, this is negative also. And so the way I think about it is it's a plus a negative. And so delta U is negative plus this, which is going to be net negative. And so the work is not like that. The work is actually, yes, it is positive, but in this case, we have to change the sign because of this equation and flip it. And so the work is net negative now. And then we add the internal energy change to it. And so when we add the internal energy change, it's going to look like this. So I was going to do this different color, but I'll just do it the same color, delta U. And so delta U is the total energy change, but we net more heat because the surroundings did work on the system. So the surroundings benefited from that. And so we actually end up, so if our gross check was 1,000, we end up with more money because of this little bonus that we got here. And so this was a little tricky because, you know, normally the surroundings did the work on the system, so that should be positive. But we take a positive times a negative, it gives us a net negative. And then we have that. We're adding the two negatives together. And so this negative plus this negative gives us this negative here. Okay, so this is kind of confusing, but it's the way. All right, this third scenario is V initial goes to a bigger V final here. And so here, this will have our delta H here, okay, which is equal to delta U minus W. Who does the work here? the system does the work. So normally, the system loses energy. The system loses energy doing the work, right? So the system loses energy doing the work, but we're multiplying that by this negative here, which means that we're going to see a net increase in energy from the work term. So system does the work, which increases the work energy here, followed by this, delta U. And so here, we should have grossed 1,000. Okay, so we grossed 1,000. Do we net 1,000? No, we actually net less than 1,000 because the system had to use energy to do work. In other words, the system lost energy doing work. But that's funny because losing usually goes down, and so actually this is gaining energy, but it's actually losing energy because of the negative sign here. Okay? And so the point of this is, it's not easy, yeah, keeping track of all these signs and stuff, right? And it takes time. And so don't expect to learn this quickly. You know, nobody learns this stuff quickly. It takes a lot of effort and time to learn this stuff. And this is why, you know, thermo is one of the most repeated classes, you know, at UCLA, that's for sure, because people end up, you know, they need a little more time to absorb it. Eventually you'll get it. All right, let's go through some more scenarios. That was exothermic with the internal energy and the enthalpy diagrams. Now we're going to go through endothermic. Endothermic, first we'll look at internal energy, and then we'll look at enthalpy. And so internal energy, U, total energy, so this is the U initial, this is U final. So we're going up, and this is our delta U here. Okay, this first scenario is V initial and V final are the same, and so delta V is equal to 0. If delta V is equal to 0, then delta U is equal to Q plus W. Under constant pressure, these are under constant pressure, then you know, Q is just delta H, and plus W. And so the work term here is 0, and so, you know, we're going to net the same. So, you know, if the price is $1,000 to do this reaction, then we're going to have to pay $1,000, right? And so it's just paying sticker price. And so this is our delta H. Delta H is the amount we actually have to pay. Delta U is the sticker price on this. All right, next scenario. Let's say we're going to decrease the volume. So V initial goes to a smaller V final. And so delta U, the sticker price is $1,000. Are we going to pay $1,000 for this? Delta U is $1,000. The sticker price is $1,000. Are we going to pay $1,000 for this? Well, you know, just fall back on the equations. Q plus W. Q is your net, delta H plus W. Delta H is what you're going to have to pay. Are you going to end up paying 1,000? Well, it depends on the work term. What is the work? Okay, delta H is positive, right? What is W? Well, it depends on delta V. Delta V is negative. If delta V is negative, right, then you just figure it out. Work is equal to P delta V. If delta V minus P delta V, work is equal to minus P delta V. If delta V is negative, then a negative times a negative gives me a positive. And so, well, a positive and a positive means this. It's going to mean your delta, you're going to have work. done by the system. And so, actually, work done by the surroundings in this case. And so the work is positive, so the system gains energy. System gains energy by having the surroundings do work on it. And so that means the actual amount you have to pay is less. And so this is where, you know, the retail price is $1,000, but you end up paying less because the surroundings, the dealer or whatever, has a discount, you know, or gave you a special discount. The special discount is they lost money and you gained it. Does that make sense? Okay, the next scenario is like this. This is where V initial is small and V final is big. And so here, you know, the retail price is $1,000. Delta V is greater than 0. If delta V is greater than 0, then work is equal to minus P delta V. And so delta V is positive, that means the work is negative. And so delta U is equal to Q, which is positive, plus W, which is negative. And so in other words, the system is going to lose energy doing the work. So system loses energy doing the work. And you have to add the work to the net to get the total. And so do you end up paying more than 1,000, less than 1,000, or 1,000? You end up paying more than 1,000. You see why? Well, why? Because you had to do extra work. System loses energy doing work. Okay, now in terms of enthalpy diagrams, it's a little bit more confusing because enthalpy diagrams has that sign switch in there, and so the change in sign makes it more tricky for some scenarios. So H here, and so we have delta H here. Delta H is our net, you know, this is how much we have to pay. Now how much we had to pay, we're comparing it to retail price. So when we compare it to retail price, well, in the scenario V final and V initial are the same, the delta V is 0. Delta V is 0, the work is 0. And so delta H is equal to delta U minus W. Well, if the work is 0, then this is just delta U. And so if the retail price is 1,000, we're going to pay 1,000 because no work is involved. In this next scenario where we go from big V initial to small V final, delta V is less than 0. So delta H here is how much we paid. Now how much we paid, how does it compare to retail price? Well, delta H is going to equal delta U plus, not plus, minus W. So how does retail price compare to what we paid? Do we pay more than retail, less than retail, or retail price? Well, in this particular scenario, what happened with the work? Who did the work? The surroundings did the work. If the surroundings does the work, then what happens with the system? Well, anyway, delta V is minus, so minus times a minus gives me a positive. This whole thing is positive. And so what should happen is the system should gain energy by having work done on it. And so you expect the system to gain energy by having work done on it, but we have this negative sign here, right? Which means we've got to change the sign on the work. And so actually the system's going to lose energy here by the surroundings doing the work, which is opposite of what you think because of the sign. And therefore delta U plus W has got to equal delta U minus W has got to equal delta H. And so we ended up paying less than retail price. You end up paying less than retail price because the surroundings offered the discount. Okay, this is the final scenario, and then look at an actual calculation. All right, so here's what the amount we pay. How does that compare to delta U, which should be the retail price of this? Well, if we look at delta B is going to be greater than 0 here. Delta B is greater than 0, so work is equal to minus P delta B. Delta B is positive, so this whole thing's negative. And so, you know, the system should lose energy in doing work. But then we have to flip the sign, and what I'm doing is I'm flipping the sign and then adding the terms. I should show that here. You know, really I should be writing this as delta U plus a minus W, or we just change the sign there. Here. And so delta H is equal to delta U plus a minus W, so we've got to do standard work. And so the system should be losing energy doing the work, but then we've got to flip the sign, so the system is going to gain energy. System ends up gaining the energy here. You know, normally it's losing energy here. So we flip the sign, and that means that we actually paid more than retail price, because the retail price is delta U. And so this is $1,000. We ended up paying more than $1,000 because of the work, extra work we had to do. So what you're going to do is you're going to memorize all these. It's not that much to memorize. You just memorize it. You're going to memorize it because you're going to get two types of problems. You're going to get qualitative problems where they're just going to ask you to conceptually tell them, you know, how does delta H compare to delta U? And then you're going to get quantitative problems. Which ones do you want to do first? Maybe you want to do the quantitative problem first. Do you want to do the quantitative problem first? Yes? All right. Versus the qualitative problem. You know the calorimetry? All right. This one is a bit tricky. Because this one, it doesn't, the work is minimal, but we're going to calculate the work for this. We'll see that it's minimal. Number 37. Missing something. Must be missing something. What else did I talk about this morning? Oh, no. I just did some other examples, qualitative examples. This afternoon we'll just do a quantitative example here. Number 37, bomb calorimetry experiment is performed with xylose, C5H10O5, solid, is the combustible substance. The data are obtained: mass of xylose burned, heat capacity calorimeter, initial calorimeter temperature, final calorimeter temperature. What is the heat of combustion of xylose in kilojoules per mole? Write the chemical equation for the complete combustion of xylose and represent the value of delta H in this equation. Assume for this reaction delta U and delta H are about the same. Okay, we aren't going to make that assumption. We're going to calculate this without that final bit there. And so number 37, first thing is, let's write the equation. C5H10O5, solid. We're going to combust this with O2. When we combust this with O2, what do we form? CO2 and water. So liquid. CO2 is a gas, O2 is a gas. So we're taking solid xylose. We'll balance it. 5 carbons, 5 CO2s, 10 hydrogens gives us 5 waters. And so this 5 times 2 is 10 oxygens, plus 5 is 15 oxygens. So we got 5 oxygens here, plus an additional 10 will give us 15 oxygens. So then it would be balanced. Okay. All right, they say that delta U, one is delta U and delta H equal? When are delta U and delta H equal? At constant volume, right? And simultaneously constant pressure. When delta V and delta U, when delta V is equal to 0, when delta, let me rephrase that. When delta V is equal to 0 under constant pressure and constant volume conditions, then we have this. Okay. Well, is delta V equal to 0 here? Pretty close, because we go from 5 moles of gas to 5 moles of gas. This is solid, that's liquid. So it's pretty close. Delta V is pretty close to 0, but not exactly 0. And so let's go ahead and figure out what delta V is here. And so the first thing I'm going to do is I'm going to figure out how much work is done in this particular reaction. And that shouldn't be too hard, because all I got to do is figure out what my V initial is and my V final. Okay, V initial, I have 1 mole of this, xylose. Is it xylose? 1 mole of xylose. And then I'm going to need the molar mass of xylose. So what's the molar mass? It's 5 times 1201, which is going to be, what, 6005. And then 10 hydrogens, 10 times 101, is going to be 10, or just 10.1. Actually, we might want 1 more sig fig for this. Might need 1 more sig fig. Yeah, actually, I'm going to go 1 more sig fig for this. So it's 10 times 1008. Going to give me 10.08. And then 5 times 1600. So what is that? 32, 74, 34, 80, 90. Right? 5 times 10 is 50, 5 times 6 is 30, so 80, right? 13, 150.13. So we have 1 mole of xylose, and it's 150.13 grams per mole. And what else do we need? We need 1 more piece of data, which is not in the problem. What is it? We need the density of xylose. Do you think xylose floats in water or sinks in water? Sinks. Do you think it's about, what do you think its density is? Most salts are around 1, most solids around, not 1, around 2. Some are more dense, some are less dense. So we could take a guesstimate, 2. But let's look up the density of xylose. 1.52 grams per cubic centimeter. A milliliter is 1.52 grams, and we want this in liters. So we got 1 liter, per 1,000 milliliter. That would be the volume of xylose, plus the volume of 5 moles of gas. 5 moles of gas times 24.45 liters of gas per mole under normal conditions. This is under normal conditions. Let's see. Yeah, we're going to assume this is under normal conditions. They start off 23.29 degrees C. This is going to be normal conditions outside of bomb, so this is under constant pressure. So we're going to imagine, if this were not in a bomb, would the volume have changed? And so now we can figure out if the volume does change. And so what is the volume of the xylose here? Did someone calculate it? Point 0.9876. All right, we'll just carry one. What is the volume of the gas? All right, this is something that's commonly done in chem and in science. When you take this volume and add this many liters, does it really change it much? No, so what we're saying is this is kind of negligible compared to the volume here. It's like this. If you have a swimming pool and you add maybe 8 drops of water, would you recalculate the volume of the swimming pool because you had 8 additional drops of water in the... No. Is it worth it? It probably wouldn't even show up. 8 drops of water, that's less than a half a milliliter. And so that's a negligible volume change. And so what the book often does is this. They ignore solids and liquids because the volume of the solids and liquids is very small compared to the volume of the gas on a mole-to-mole basis. And therefore what they do is they usually just ignore this, because the volume of the gas is like 1,000 times more. Something like that. But is that an error? Yes, that's an error. If I could just call this 0, that's an error because this does have volume. Right? This is not 0 volume. The xylose is going to have volume. But is it a significant error? No, it's not a significant error. And therefore, maybe it's okay. And so V initial, what is V initial going to be? V initial is going to be 122 point, add 98 to this. Add 9, 14, so 3, 4. 122.34 liters. So yeah, it's a little bit bigger, but not by much. As far as the percentage goes, it's not much. All right, that's my V initial. What's my V final? Let's go ahead and calculate the V final. Next. So calculating V final, I have 5 moles of gas times 24.45 liters per mole. And then I have 5 moles of water. Here it's 18.02 grams per mole. And density I don't have to look up, it's just 1.00 grams per milliliter. So milliliter is 1.00 grams. And then there are 1,000 milliliters per liter. And so this was 122.25, was it? 1.256? No? Just 2.5? 122.25 liters plus, how much is this going to be? 0.0901. Now compare this, you know, the volume of this was around 0.09, the volume of this is around 0.09. And so there really wasn't much change, you know, going from a solid to liquid. The density of this is 1.5. The density of this is 1, you know, although we have, you know, a lot more atoms here. You know, we got 5 moles worth here. And so it doesn't really change much. And so this comes out to 122.3 122.34. And so delta V here, delta V is equal to 122.34 minus 122.34, which gives us about 0. We'd have to go to more decimal places to figure it out, but we'll just say about 0. So if delta V is about 0, then we know something here, you know, because this is under constant pressure conditions. And so if delta V under constant pressure conditions, that means delta U is equal to delta H. And so this is pretty accurate. You know, delta U is equal to delta H according to the sig figs of our calculation. Okay, what do we do when it's not equal? And so let's take a look at another example here. Let's try some others here. Okay, they give us this, salicylic acid has been suggested as a calorimetry standard. In heat of combustion, its heat of combustion is minus 3.023 times 10 to the third kilojoules per mole. So let's take a look at salicylic acid C7H6O3, number 42. C7H6O3, solid. So if we burn solid salicylic acid, an O2 gas, it's going to yield CO2 gas plus H2O liquid. And so we have 7 carbons here. We're going to get 7 CO2s there. That's 6 hydrogens, so we need 3 waters. This is going to be 7 times 2 is 14, plus 3 is 17 oxygens on the left. We have 3 here, and so 3 will need 14 here. We need 7 oxygens there. Okay, when we look at that, what can we say about the what can you say about delta U and delta H? Well, looking at the moles of gas, we go from 7 moles of gas to 7 moles of gas, meaning that whether we do this under constant volume or constant pressure, there's not really going to be a change. You know, there really has to be a change in the moles of gas in order to generate pressure in the container or vacuum in the container. And so in this case, you would say that delta U and delta H are pretty much the same. You know, not exactly, because there's just slight volume differences, but you'd have to go out quite a few decimals to get it. And so the work is minimal here. And so again, we have this scenario where it doesn't happen. Let's take a look at another one here. Number 41. Number 41 is naphthalene, C10H8. C10H8, solid, is combusted in a bomb, O2 gas. This is going to form CO2 gas plus H2O liquid. So we got 10 carbons, so we'll need 10 CO2s. 8 hydrogens, so we'll need 4 waters. And so this gives us 20 plus 4, 24 oxygens over here. So we'll need 12 oxygens here. Okay, now let's take a look at this here. When you look at this, I look at this and I go, delta V, is it close to 0? No. Delta V is going to be less than 0 because we're going from 12 moles to 10 moles. So we're losing 2 moles of gas, which is like 50 liters. You know, 50 liters is a lot of volume change. You know, if I had a 50-liter Coke can, that would be crushed if you suck out the gas by the surrounding. And so definitely there's some work being done by who? By the system or by the surroundings? By the surroundings. And so what does this look like? You tell me. Well, let's look at this in terms of internal energy diagram. Tell me what this is going to look like. Where is delta U? In terms of internal energy diagram, this is combustion, it's exothermic, so this is delta U. Now, what is delta H going to be? Well, who did the work? The work was done by the surroundings. That means who gains energy by the work done by the surroundings? The system gains energy, W. We don't have to worry about this tricky sign because this is just straight. The work, and therefore, Q is like this. QP or delta H. And so in this case, delta U is not equal to delta H. And so here we're going to figure out what both delta U and delta H are. But we're out of time, so we can't do that today. We'll figure it out next time.